Yeah, it's just that my clicker is not.
Try now with the clicker.
No, no difference. So the clicker's turned on. Let me turn it off and then turn it on again. So you can either have the audio or you can have the slides. What do you want?
Try now.
No, it's definitely recognizing the clicker. It's just not.
So do you have to set up a clicker?
No, it just happened. It worked a few seconds ago. So we got a new USB hub so we can get everything synchronized on one machine. And we are,
Stream is on.
okay, this is,
Oh no. Oh, it's showing up. It moves in this window.
Okay. So then. Now try it.
nope.
It clearly moved in this window.
Try now.
No. Really weird.
Exit this. Yeah, clicking the button I think works in this state.
Okay. Oh yeah, it does. Okay, then let's just work off this one, right?
Hold on, try it.
Yes, work.
Hey, there we go.
Wait, now. And now it doesn't.
I think the moment my mouse left there, it stopped working.
Okay, so it has to stay, the mouse has to stay on there. That's it.
Okay.
Just leave the mouse on.
All right.
Wait.
Let
And-
me adjust the.
We need to go back to it to fix the image on the screen.
Oh, there's so many like things there.
Oh, yeah. Just love Microsoft.
We were here half an hour early trying to get this working.
So is the stream on?
Stream's on.
Okay, perfect. Now can you move the mouse onto the whatever screen, please, so I can.
Yes. Give us 1 second.
No, even re-adding it does that. It's like dependency now. It's that one, but it doesn't work. That one's the prompt one.
All right.
Yeah, we need to get started.
All right.
We're going.
Wait. So what happened? It was working. Then just
Oh, yeah, this is good enough now.
okay. Just move the mouse on it and
This is
wait. Now that doesn't work. Ah. So,
that's us.
oh. So what happened between?
So the issue is that once we go to the presentation, then we come back and try to have it refresh on the stream, but the stream is showing the wrong image. So we're just going to control it here. We're going to plug in your laptop.
Okay.
And then we're going to go off.
Okay. Let's go with the old setup and figure this out later, right? And I assume that the audio will be captured off the laptop.
Yeah.
Okay. I'm trying to. Yes. Right. Now the audio has to be set up again on the laptop.
There we go.
Perfect.
All right. So we'll set up the stream and manage it on our own. But you can
Yes.
get started.
All right. So everyone, thanks for your patience. Yes. 2, 4, 6, 8, 10, 12. So it shrinks every day, right? After spring break, what usually happens is that the first class after spring break tends to be empty, and then people realize that you can get away with not coming to class, and then towards the end I'm teaching 2 people, but there are like 100 people registered. So I hope that doesn't happen. Anyway, what we're going to be talking about today is trying to see what the network actually learns. What does it represent? We've gone through this in the as part of the homeworks. We've sort of implicitly seen these issues before. Let's just sort of concretize it a little bit. Now here's the basic idea. Our purpose was to try to when we were learning a network, the problem was this: you're given a collection of input-output pairs, and the purpose is to try to learn the function. The purpose of learning is to try to learn the function that relates the input to the output. We've already seen this. And when we are learning for classification, the function specifically has a discrete output, which is where the network tries to learn the classification boundaries that separate the training instances. As we know from our homeworks, we don't actually have a discrete output. We get something softer. We'll see why. But the objective here would be to learn boundaries of this kind, where you say that you'd be given all of these red and blue dots, and the idea would be to try to find those gray lines that separate the red class from the blue class. In reality, what does happen is that the data are not going to be cleanly separated. So you're going to have blue dots inside the red region, the red dots inside the blue region. So considering that the data that you present are already mixed up, what does the function really learn? It's not learning the boundaries, because there are no clear boundaries, right? So now here's a trivial linear example. It's good to explain with linear examples. Here's what really happens. In a linear example, here's what you really get. You're going to have data. This is a two-dimensional data, where you have a red side to the data. You have a green or a blue side to the data, depending on which picture you're looking at. But then you also have some blue dots on the floor on the red side, some red dots on the ceiling on the blue side, and there's no clear line or hyperplane that's actually going to separate the red from the green or the blue. They should have been blue, mixed up. But there's no real clear line that you can draw saying everything to one side is one class and everything to the other side is the other class. Now, in a 1D example, if I were to bring it down, here is the situation you'd find. Here, all red dots. So your training data would comprise xy. X is one-dimensional. Y is the value that you're trying to predict, the class variable. And so the class variable would be either 1 or 0. So if I just plotted the scatter, you're going to get something like this. All the red dots at y equals 1 represent instances of class y1. The blue dots at y equals 0 represent instances from class y equals 0. Now, if I wanted to draw a linear separator, or if I wanted to just have some simple way of separating one class from the other, that is simply going to be a threshold, a vertical line, so to speak, right? But in this case, no threshold is actually going to cleanly separate the red and the blue dots. Now, I can learn a function of this kind. And do we really want a function of this kind? Most likely not, right? But I could learn a function of this kind, which peaks up and gives you a 1 for each of the red instances, and a blue for each of the and a 0 for each of the blue instances. And while it does capture your training data perfectly well, it's not generally not the desirable kind of function. But then to understand why this is not a desirable function, let's take a look at a specific instance. So let's say I have a situation here where I have red and blue dots at exactly the same point, right? And specifically, I say I have many red instances and many blue instances at exactly the same point. So I have 90 red instances and 10 blue instances. What must the output of the function be? Must the output be 1 because red dominates, or should be 0.9 because, if I take the average of all of these instances, the average value is 0.9. Now, intuitively speaking, this 0.9 gives you is much more informative. It tells you something about the data. What it's actually giving you is an estimate. If you thought of these instances as random variables, it's giving you an estimate of the probability of 1 given the input x. So for that specific x, what fraction of all instances that have that particular value of x are going to be 1, right? So this is also the average. It turns out that the two are going to be the same, right? Now this is potentially much more useful than simply saying I must assign this to red. This carries more information. It's also more realistic. It gives you an idea of your confidence in what the output must be. Now, let's say instead of just having all of the red and blue values at exactly the same point, it turns out that the blue values are just an epsilon off from the reds, and the epsilon is really tiny. Must your estimate change? Must your output change? Now remember that just when I move things off by epsilon, I can now draw that crazy function that I showed you earlier, right? But it doesn't make sense. I can make that epsilon as small as I want it to be. And clearly at some point of time, regardless of how close they get, I can keep making this crazy function finer and finer. It really doesn't make any sense to have something that goes down for the blues and up for the reds. What you really want to know is that in this range, red occurs 90% of the time. So for x somewhat in this range, the probability of x is 0.9. This is the kind of information you'd really like to see, right? So let's consider the problem somewhat differently. At each point, let's look at a small window about that point, which accounts for the fact that you can have an epsilon jitter really shouldn't be changing what the network tells you. And let me plot the average of the value within the window. Now this is an approximation of the probability of y equals 1 when x takes that specific value, or x takes a small sliver of, falls within a small range, which is a small sliver around that particular point, right? So as I move left to right, I'm going to get something like this. Initially, at every x, all points are going to be blue. Then at some point, you're going to begin seeing some instances of red. And then as you keep moving further right, you're going to see more and more red. And eventually, you're going to run out of blues, and then you'll see only reds, right? So this blue sequence of blue dots, in fact, if I slit continuously left to right, that's going to be a curve of this kind. And that curve is really giving you an estimate of the probability of 1 given x, right? So a nice function which actually models this kind of probability is the logistic function, where we say the probability of y equals 1 given x is 1, this is the standard logistic function, 1 over 1 plus e raised to minus w0 plus w1x, right? So look at what happens when x is infinity. If x is infinity, you get 1 over 1 plus e raised to minus infinity. E raised to minus infinity is 0, so that becomes 1. On the other hand, if x is minus infinity, then e raised to, that becomes 1 over 1 plus e raised to infinity, which is 0. And so as you go from left to right, it goes monotonically from, the function goes up monotonically from 0 to 1. And at the value where, and where will this function take a value of 0.5 exactly? That's going to be where w1x plus w0 equals 0, right? So, and at that specific location, so can w0 and w1 both be positive in this case? Clearly can. You just choose your threshold, right? So, but at that specific location, you're going to get 1 over 1 plus e raised to 0, which is half. And so that location is going to be right here, where x equals minus of w0 over w1, right? Now, I can scale these things. I can get the same kind of shape for different values of by just scaling the w's. So if I multiplied every w by, say, 100, I'm still going to get this smooth shape, except the entire function is going to stretch. And depending on what I multiply the function w with, if I multiply it by a large number, 100, it's going to shrink. If I multiply it by 0.1, it's going to stretch. So there's that scaling, how the function stretches. There are two parameters over here, exactly where the function is centered and how much it is stretched. And those two together are going to give you the shape of this curve, which will tell you what the probability of y being 1 at any particular value of x is, right? Now, let's go back and look at our perceptrons. Our perceptron with a sigmoid activation, a logistic perceptron, is just your standard logistic function, right? So a sigmoid perceptron with a single input models the a posteriori probability of the class given that single scalar input x. That's going to be a function of this kind. That's just my representation of the perceptron. X goes in. The output of the function is 1 over 1 plus e raised to minus w0 plus w1x, right? So we've used this. We've actually used the multi-class version of this, but I'm going to continue talking about the single class version. Now, if I have a two-dimensional example, this is the same figure that you saw. Earlier, you have blue dots on the floor. On the red side, red dots suspended at y equals 1 on the blue side. No line or hyperplane is going to clearly separate the points. But then I can try to fit a logistic regression, two-dimensional logistic regression over two variables, a bivariate logistic regression on the scatter, and the function is going to look something like the surface to the left. This is just a perceptron with 2 inputs and a bias, right? So this is going to be a sigmoid perceptron with inputs x1 and x2 with their corresponding weights w1 and w2 and the bias w0. And the weights w1 and w2 are now what you will notice is that this function is a curve, nice smooth curve. Now, if I want to take a hard decision and say that, I want to set a threshold on the output of the function beyond which I'm going to call the output a 1, and if the output is less than that, I'm going to call it a 0. Regardless of what threshold I choose, the resultant decision boundary is going to be a line, because basically when I choose any threshold, you're basically saying summation wi xi plus w0 equals some value. That's going to give you the equation of the line or the hyperplane, which separates the one side from the other. So this is really a linear classifier, which gives you a linear decision boundary between the classes. And the entire function itself gives you a softer version of this decision, which is a probability, right? Now, if you want to estimate this model, what would you be trying to do? You're going to be given many, let's start off with trying to estimate just a simple logistic function, right? That is a single perceptron with a sigmoid activation. Then you're going to be given input-output pairs. You're going to be given many xy pairs represented by the dots over here. And our task would be to estimate the w0 and the w1, which give me the shape of the best curve that estimates this probability of that estimates the probability of y equals 1 given x. Now, I want you to observe over here in the previous slide that w1 and w2 and w0 together actually decide the line. That line is basically the line that I've shown over here, which separates the yellow from the blue red regions, which is a decision boundary that I get by assigning some threshold to of p of y equals 1 given x. That's always going to be a line or a hyperplane in higher dimensions. And the orientation of that plane is given entirely by these vectors, by the vector of weights, which is a normal to the plane, right? So in the case of a scalar, that w1, the w0 and w1 are going to decide where the output actually becomes a 0.5, but you could use other thresholds. Anyway, between the two of them, they actually decide the shape of the curve that you're trying to fit to the points. Now, and if you want to find the if you actually want to find the best fit curve to those points, what you really want to do is to estimate these weights, w1 and w0. Now, to see how this is done, it's more convenient to think of the output in terms of 1 and minus 1 rather than 1 and 0, right? So in that case, let me say if I represent it using a y equals plus 1 or minus 1 notation, then p of y equals 1 given x is going to be given by this term, right? Observe that now the vertical axis is going from 1 for the blues to minus 1 for the reds. And p of y equals minus 1 given x is simply going to be 1 minus this guy, right? Which works out to 1 over 1 plus e raised to plus w0 plus w1x. So all that changed between the probability of y equals 1 and the probability of y equals minus 1 is that the sign of the argument of the exponent changed. So I can combine the two and write it in one common form and say that in general, the probability of y given x equals 1 over 1 plus e raised to minus of y times this line term, linear term. And you see how this works out. So if y is 1, this equation maps out to this guy over here, right? And if y is minus 1, it maps out to this other term to the right. And now, if I give you a collection of training data points, which comprise x, y pairs, and x's are vectors, they don't have to be scalars. Y's are the binary, actually plus 1, minus 1 class values, not 0, 1 in this case, as I've written. Then, so that's a bug. Then the joint probability of x and y of your training data is simply going to be, assuming that all of your training data instances are independent of one another, this is simply going to be the product over all of the instances of the probability of the individual data points. Using Bayes' rule, I can separate this guy, p of x comma y, as the probability of y given x times p of x, right? So this entire term is going to become the product of, assuming that if I'm representing P of y given x by the logistic function, this entire thing is going to become the product of over all the training instances of the logistic function applied to each of the inputs times the probability of the x itself for that input. And further, I can segregate these into two components. So I could take the log of the probability of the training data. And if I take the log of the probability of the training data, you have the log of the P of x coming out on this side. And the second term, which is the log of the probability of y given x, is a function of the weights. And now, if I want to, now a standard approach for training statistical models, probability distributions for data, is to find the value, parametric probability distributions for data, is to find the set of parameters that maximize the likelihood of your training data. So if I were to perform maximum likelihood training data, estimation over here, the estimates for the weights is going to be the argmax over the weights of the log of the probability of the training data, right? Maximizing the log of the probability is the same as maximizing the probability. And now, if I go back to the previous slide, observe that the log of the probability of the training data is the log of the x probability, the x values, minus the log of the logistic function applied to each of the xy pairs. So when I'm maximizing the negative of the log of the logistic function, this is the same as minimizing the logistic function itself. And P of x doesn't depend on the weights. I can ignore it, right? So this means that my best fit for the parameters of this logistic function is simply going to be argmin over w over the weights of the sum over all training instances of the log of the output of the logistic function computed for the appropriate outputs. So observe again over here that for any particular training instance, if my output is 1, then I'm going to be only considering log of the logistic for y equals 1. If for any particular training instance the output is -1, I'm only considering the log of the logistic computed at y equals -1. So what does this look like? You're really just summing the log of the probability assigned to the class label for each of the training instances. And you're minimizing this log probability, right? And what does this look like? This looks a lot like minimizing your cross entropy or your KL divergence, right? So this is exactly what you're going to be doing. You're minimizing the KL divergence between the desired output y and the actual output produced by the network. So this is basically, this is what we're actually saying, right? Now, you can't solve this directly. You need gradient descent. All that works out. But then what we've seen over here is that we've seen how we can estimate a logistic function. And specifically, we've seen that a logistic function, a single perceptron with a sigmoid activation is just a logistic function. If I'm trying to fit the sigmoid to my training data, then what I'm really doing is performing a maximum likelihood estimate of a fit of the logistic function to my training data, right? So this is what we will come back to later, okay? Now let's go back and look at this problem again. Here, this is a nonlinear classifier. This is no longer a linear classifier. I'm not actually trying to separate the x's and the y's with a single line, right? On the other hand, the classes are not separable. So I have some blue dots in the red region, and some red dots in the blue regions. So let's simplify it for now, and let's go back to the situation where the classes are actually linearly separable. Now the network must learn to classify between the two outputs, right? If I have a sufficient network, what I mean by a sufficient network is a network which has sufficient architecture to actually classify, to classify the reds and the blues cleanly. So it's a network which can actually draw these two polygons. We've seen earlier in class that that kind of network would have the sort of architecture I have shown to the right. The first layer is capturing all the lines of the polygons and the individual polygons. The second one is capturing the polygons and finally ORing the polygons, right? This is a sufficient network. Now, consider what's happening at the very final neuron of this network. The output neuron for a binary classifier is just a logistic function, right? If I'm using a sigmoid as the activation, it's just a logistic function. So if this network is performing a perfect job of classifying the blues from the reds, we know that the output is a linear classifier, right? This means that at this point, the data must be nicely linearly separated. They must be linearly separable, right? So in other words, if I look at what happens, what the outputs of those two neurons are going to be just before the final output, and if I plotted a scatter of those guys, so the scatter of the input after it has been passed through the network, so the input has now become two values, right, y1 and y2, and if I plotted the scatter, if this network is doing a perfect job of separating the y blues from the reds, then that means that at that layer, the blues and the reds can be separated by a hyperplane or a line, right? So now this means that at the output of the penultimate layer, the layer just before the output layer, the classes must be linearly separable, right? So what does this tell us about the rest of the network? The rest of the network is just this crazy nonlinear function that transforms data from nonlinearly separable classes to linearly separable features, right? So you can think of this network as something is off. My slides are off. Okay, so I don't think these are the latest slides I've got. Anyway, is this what you've got on the streaming? The same slide? Okay. So there's some stuff missing. Anyway, so what we mean is I can think of this whole network as two components, right? The first is the output, which actually performs the classification, and everything below the output as a transformation that transforms data from non-linearly separable classes into a space where the classes are now linearly separable. So once I do that, at the y level, the data are linearly separable, right? I can attach any linear classifier. Once I have a feature computation network which takes classes which are kind of mixed up with one another in a very nonlinear way, and it has this magical ability to just separate these things out and bring them into a space where the classes are now linearly separable, I can attach any linear classifier on top of it and perform my classification. And in fact, as we know, in fact, if you're going to be performing linear classification, maybe a logistic regression is not the best classifier you would want. You could use a support vector machine on top of these features to get classification with a margin, right? The output need not be a perceptron, simple perceptron. So now this is true for any sufficient architecture, not just the optimal sufficient architecture. Meaning, if I have any network that is sufficient for the output to be perfectly classified, and for these decision boundaries to be for these decision boundaries to be captured, these pentagons, that means that network is actually transforming my input features, which lie within crazily shaped decision boundaries, into a space where the inputs for the various classes are now linearly separable, so that the final layer can perform the linear classification. Now, what if the network doesn't have sufficient capacity to model this particular decision boundary? So for example, let's say I'm trying to do these double pentagons, but in the first layer I have one neuron less. Now this, if I have one neuron less, that network is not going to be capable of actually drawing those double pentagons. It's going to, so in that case, what would it do? It will fail to separate, but it's still going to try to come as close as possible to making those inputs linearly separable, right? And in fact, if you think about it from that perspective, simply trying to stick a perceptron at the top maybe not as optimal as, say, trying to stick in a support vector machine with a slack variable, which accounts for some instances which might be misclassified and tries to minimize, explicitly minimize the distance of the misclassified instances from the boundaries, right? So now if I want to write it mathematically, I can say y out, which is the output of the network, is the logistic function applied to the y's, which are the output of the penultimate layer, right? And I can write it in vector form, which is going to be 1 plus exponent of b's, whatever bias it has, plus w transpose times f of x. What is f of x? F of x is the gray box, which is the entire network until and including the penultimate layer, the second to last layer, right? And now the data are linearly separable in the space of y, and the network until the second to last layer can be thought of as a nonlinear function that converts the input space of x into a feature space y where the classes are maximally linearly separable. So now you can literally think of the neural network as two components. One is a feature extractor and the last is a linear classifier, right? That is in fact what is happening within the network, right? And this of course brings you to the story so far. A classification MLP actually comprises two components: a feature extraction network that converts the inputs into linearly separable features or nearly linearly separable features, and a final linear classifier that operates upon these linearly separable features, right? So for binary problems, as I mentioned, using a support vector machine with slack may be more effective than just a final perceptron, and you could do it in multiple ways, right? We could actually do this in a greedy way where you can just train a standard multilayer perceptron, and then once you've trained a standard multilayer perceptron, get rid of the final classification layer, you now have a feature extraction module that actually explicitly makes the classes some almost linearly separable, and then you can just go ahead and train a support vector machine on top of it. Or you can actually jointly optimize it. So the objective function that you optimize to train the network itself might be the max margin objective function that you use for support vector machines, specifically if you're using slack variables, right? Exactly how you will do this, I'll leave this as an exercise too, but this is obviously, this is very obvious, and you can actually see how this would happen, right? So now you're actually you would have a maximum margin version of a multilayer perceptron. And again, there's nothing magical about multilayer perceptrons. Everything I'm talking about is a concept that extends to every form of neural. Now, how about the lower layers? What happens? So we've just looked at what happens in the penultimate layer. But if I go one layer down from the penultimate layer, what happens? They too compute features. But then, what kinds of features? It's kind of hard to write out the math in the most generic setting. But as an intuition, this hypothesis kind of somewhat holds, in that if I have linearly separable classes, the classes in general can be thought, they may not, if I have classes, the classes may not be linearly separable in the original space, but you can think of them as being linearly separable on some crazy manifold within the original space. So you can think of having some really crazy surface that you're drawing within the original space, and the data, so that actually the data live on. And now if you straighten out that surface, on the straightened out surface, the classes would be linearly separable. And that's what the final layer is going to be working on. So if I think of it that way, then you can think of the layers as sequentially straightening out this crazy data manifold, such that you eventually get a flat manifold on which you can perform linear classification. So we have some examples over here. This is a two-dimensional example where we are trying to build this classifier for the circle. It doesn't look like a circle because MATLAB gives you stretches the x-axis out. And so I have 6 panels. This has how many? This is a 2, 3, 1 neural network. So the first layer, you have 2 dimensions. Then I have a 2 input, 2 neuron. I have a 2-dimensional input. So the input layer has 2 neurons, or 2 values. Then I have 3 hidden variables, and then I have the final classifier. And what is going to happen after is for the first hidden layer, you're going to go up from 2 dimensions to 3, right? But the data are a circle, 2-dimensional circle. So when I multiply my circle by some weight, and then I add a bias to it, I'm just going to get an elliptical disk in 3-dimensional space. So this is the input to the second layer, to the hidden layer. This is the output of the hidden layer, because the hidden layer is going to distort it, right? And then this is the input to the final output layer, which is just one neuron, right? That you're going to actually be performing classification on. And this is the final decision boundary that you get in the original 2-dimensional space, right? So when I initialize everything, just randomly, the disk is going to get shifted to some arbitrary point. The output of the first layer is going to convert that disk. It's going to distort the disk in some crazy way. And then the second layer, which zaps things down, when you collapse it to a single scalar, this is what the scalar looks like. And you see the central regions are all blue. All the blue values fall in the middle, and the red values fall out to the side. And if I try to draw a decision boundary based on on this initial network, the decision boundary is this guy, which is nothing, nothing like the original circle, right? So now let's see how this thing evolves as you go through the network, if I can. Yes, sir. You see this crazy thing, right? So what is happening over here is that the disk is sort of moving around, and then eventually the network learns to segregate all of the. Look at what happened at the output of the first hidden layer. All the blue stuff went to one side, all the red stuff went out to the other side over the evolutions. And then when you project it down, the red and the blue are kind of nicely separated. And the decision boundaries, if I'd continued the training for several more epochs, it would actually end up becoming a circle. This whole thing will take a few seconds if you can run it. I mean, it's kind of silly that I ran out of patience at 200 epochs, but this was code written by Anders. But you see what is happening over here, right? I'm starting off with this surface, and I'm sort of moving it up into some other higher dimensional space and mangling it until the classes become linearly separable. And now I can just apply a linear classifier. Very simple, right? So this is what you would expect to see. Now this is a very simple example where I have only, it's a 2-dimensional input. We're all familiar with it. Where it's trivial to visualize stuff, and it has only one hidden layer. But then let's go to a more, and maybe it doesn't tell the entire story. So let's go to a more complex setting. This one is for Sapphire, and this has many classifiers, many layers. You can see what happened over here. So I don't remember the actual architecture of the network. It has several layers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 layers, and then a final classification layer. And you can see what happens. All of the classes are mixed up in the original data space. All of this is with principal component analysis down to 2 dimensions, right? As you go through the layers, what is happening is that the classes are beginning to move out. Now you don't actually see the manifolds separating out because it's a 2-dimensional projection from a very much higher dimensional space. But eventually, so you see that even in this 2-dimensional projection, now the classes have sort of nicely separated out, and they become linearly separable, right? So here it is again. And as you go through the classes, you can see how the thing sort of wiggles around and converges to this setting, right? Or here is the same thing. Now I'm actually sure this is a PCA into 3 dimensions, so maybe things are more visible. And observe what's happening specifically at this location, which is the penultimate layer. And you will see things separate out not just horizontally, but also vertically, although it may not be immediately visible because the perspective is not quite right. But take a look. So you saw how all of the classes sort of separate out. And the yellow is actually on a different level than these guys, and so the yellow also is linearly separable, right? So as you go through the layers, all of the classes sort of the manifold basically gets opened up and untangled, so to speak, the data manifold, so that the classes actually become linearly separable. And then finally, when they are as linearly separable as they can possibly be, the final classification layer is going to operate on those and draw nice linear classification boundaries, right? Now, when the data, that was for when data are separable. When in the CIFAR they are not, but they are almost separable, right? But let's take something more obvious. When the data are not separable and the boundaries are not linear, like in this case, which is more typical, a more typical setting, then what really happens? The feature extraction layer transforms the data such that the posterior probability might now be modeled by a logistic, right? So over here, what you really want is that in this space, as you move into the pentagons, you want the probability of red to keep increasing. As you move outside the pentagons, you want the probability of red to keep going down, right? Now, it's not clear how you would do it in the space of the in which the pentagons actually reside. But what the network will do is to sort of untangle these things into some space where the decision boundaries, kind of the best decision boundaries, somewhat is linear. And now in that space, you fit a logistic regression. And then you can compute a posterior probability for the classes in that space. So the feature extraction layer is again separating things out to make assignment of probabilities using a linear classifier possible, right? So what happens is that the feature extraction layer transforms the data such that the posterior probability might not be modeled by a logistic, and the output logistic at this point now simply computes the posterior probability of the class given the input. This is true regardless of whether it's a binary classifier or a multi-class classification problem, right? So what this means is that the output of the data now is actually the probability of the class given the input. Because what is the logistic computing? We saw this, we've been seeing this through this lecture. The logistic actually computes the probability of the class given the input, right? And so it's going to compute the probability of the class given the input to the logistic. The rest of the network is just a feature extractor. We can think, so overall, the network itself is simply computing the probability of the class y given x. And for multi-class networks, it's going to be a vector of a posteriori class probabilities. Now, when we spoke about the logistic function and learning the logistic function, we said that the logistic function is actually learned using a maximum likelihood estimator. So when you use a cross entropy loss, if I think of a simple a network comprising just a single perceptron, right? So it's not really a network anymore. And I use a cross entropy loss to train that perceptron. What I'm really performing is a maximum likelihood estimate of the network. That doesn't change just because I have a more complicated feature extractor underneath the perceptron. So even here, what we are really performing is a maximum likelihood estimate of the network, given that the network can be thought of as a statistical model that captures the probability distribution for the data, right? So the network is now a parametric model for the probability distribution for the data, such that given any input x, it provides p of y given x, and we are really performing we are actually doing a maximum likelihood estimate because you're maximizing the joint probability of the p of y given x times p of x, except that the probability of x itself factors out. So you're actually computing, you're learning a model for p of y given x. That's what the process of training the neural network actually does, specifically when you're using the cross entropy loss. Right. Questions? No? Okay. And any of you read this book? It's an old one. It's called Illusions And I have this, it has this beautiful final line. It's lots of philosophy. And the last statement of the book is, everything in this book may be wrong. It's from the 80s. I highly recommend it. It's a good book. Anyway, everything I say may be BS, right? Why is that? There's nothing stopping me from learning a crazy function of that kind, right? So a sufficiently detailed architecture can separate nearly any arrangement of pairs. I'm saying nearly because the specific arrangement where it cannot separate is if the x values are identical and the y values are different. But anything else, I can always kind of overfit something and learn a model. So the correctness of the model and the various intuitions that I just explained are subject to many parameters like the regularization, the detail of the network, the training paradigm, whether it is converged, etc. So eventually, all we can say is that it is our objective to learn P of y given x, and we want to learn this as robustly as possible so that it generalizes to data that are not part of the training set. But if you're only focusing on the training aspect of it, you're perfectly liable to get something like this, which is probably absurd. And how you avoid an overfit of this kind and end up with a statistical estimator that represents your data best ends up being a function of many factors, including how you actually optimize the network, right? So that's a caveat. Now, so we've looked at what the network actually does. The network has two components. The first is a feature extractor, which tries to make the data linearly separable. And the second is a linear classifier. And when you look at it that way, you can use any linear classifier at the output, any optimization paradigm that actually optimizes the linear classifier. And you can also think of the network for non-linearly separable classes as something that computes the a posteriori probability of the classes given the input. And if you're using the cross entropy loss to optimize the network, specifically you're using a maximum likelihood estimator to estimate the parameters of the network, and the network itself is a parametric function, a model of the a posteriori probability distribution, right? But then here's a different perspective. We've seen what the network learns at the output. What happens just before the output? So at the hidden layers themselves. For that, let's recall the basic perceptron again. The basic perceptron was something like this. You had a vector going in, and the output was 1 if the weighted sum of the inputs exceeded a threshold, 0 otherwise. But what did the weights tell us? We saw this in the first or the second class, right? We've seen this before. The neuron fires if the inner product between the weights and the inputs exceeds a threshold, right? So specifically, we saw early on that I can think of this argument of the network of the threshold function as the inner product between the weight vector and the input vector. And if this inner product exceeds a threshold, the neuron's going to fire, which means that if the angle between the weights vector and the input is lesser than a threshold, the neuron is going to fire, right? Alternately stated, the neuron fires if the input vector is close enough to the weight vector, or if the correlation between the weight vector and the input vector exceeds a threshold, right? So we saw that if I had a pattern of weights, now the weights can be arranged in the same live in the same space as the input itself. So if I'm classifying images, the weights also represent images, at least in the first layer, right? And the entire network building up to any point is looking for image patterns that it will respond to, right? Now, so the weights, let's say the weights can be arranged in this pattern which looks like the number 2. Then a perceptron is going to fire if the correlation between the input presented at the perceptron and the weights exceeds a threshold. So if the input was something like this, the correlation would be 0.57, it wouldn't fire. If the input was something like the figure to the right, which looks a lot more like a 2, the correlation is much higher. That's 0.82, and then the neuron and the neuron will fire. So the perceptron is a correlation filter. We've already seen this, right? Now, so building on this, we saw that the lowest layers of a network. So basically, the perceptron is a correlation filter which detects patterns. It's going to detect patterns which look like the arrangement of weights, right? So if I were to be building, for instance, a multi-layer perceptron which looks at these old LED displays and tells you whether this is a valid digit or not, then you would expect something like this. You would expect the lowest layers of the network to detect significant features in the signal, like horizontal and vertical lines. And then the additional layers, later layers are actually going to be composing more and more complex patterns from these. And detection, eventually you're going to be detecting things, composing patterns of which look like the classes that you're trying to detect. And if those are detected, the neuron will fire. So now here you have two different perspectives, right? In the one case, I told you that the lower layers of the network are just a feature transformer which converts the inputs such that the classes are linearly separable. But now I'm saying something else, that these are actually feature detectors, and clearly there's the two are analogous, right? But then let's go back and look at something else. Suppose I just looked at the outputs of the first layer. The outputs of each neuron in the first layer is detecting a specific kind of pattern that may have occurred in the input, right? So if I detect some patterns, if I put those patterns back together, I can expect to get part of the input back, right? Would the input be perfect? No, because really the network is optimized to recognize digits in this case. So it's only going to learn to detect digit-like, obviously digit-like, or obviously not digit-like features. And so anything that you get, that you reconstruct from these detectors, is going to look like maybe a cleaned up version of the input, where it retains only the clearly digit-like or the clearly non-digit-like features of the input, right? But then, what if I try to train the network to actually construct the input? So in this case, the neural network is being trained to predict the input itself. This is what we will call an autoencoder. It's taking an input and it's learning to recreate itself. Now, this has two components: an encoder, which learns to detect all the most significant patterns in the input, and a decoder, which learns to put these things back together to reconstruct the input, right? Now, let's take the simplest version of this, where I have only one neuron. So I have inputs going in, I have a single neuron, and then which detects a particular pattern, and then I'm going to try to reconstruct the input from that pattern itself. So in other words, these weights represent the pattern that's being detected in the input, right? So if I'm trying to reconstruct the input by just saying this is the pattern, I've found it, then the output weights are going to be the same pattern, right? You'll be reconstructing exactly the same guy. So if I did that, then let's take the simplest case, where the neuron in the middle only has a linear activation, right? If the neuron in the middle had a linear activation, and I trained this little network, which is not even a network, it's just a single neuron, right? What would it learn? I'm going to try to learn it by minimizing the error between the reconstructed output and the input, because I wanted to learn the most characteristic feature of the input and reconstruct the input in terms of this most characteristic feature. So what I would do is I would define the divergence as the L2 error between the input x and the recomposition x hat, which I can rewrite as x minus w transpose wx, because wx is the input to the first neuron, which has a linear activation. There's no further transformation. And then w transpose is basically, I'm taking whatever the strength with let's say the strength with which the input pattern has been detected, and scaling that same pattern to reconstruct the output, right? So now if I try to minimize this divergence, that's just trying to minimize the squared error between the original data and w transpose w times x. This equation must be familiar. What does it look like? Anyone? This is just PCA, right? You're literally just trying to, this is just, in fact, I have it written at the bottom of the slide. It should have been easy for you, right? You're obviously not paying notice. But then what does the autoencoder really find in this case? It's finding the direction of maximum energy. And specifically, if the input has 0 mean over the ensemble, it's finding the direction of maximum variance. Basically, you're finding the principal axis along which the data varies, and you're mapping all data points onto the principal axis. So if the dots were the scatter of your data points, what this would find is a line of that kind, and say all data are that line is the principal characteristic along which most of the energy in my data lies, and every single data point, when it's reconstructed, is being reconstructed as some extension of that blue line, right? Now here's something interesting. So let's say I went ahead and trained this network, and then I threw away the encoder portion of this, and now I just have the decoder portion of this. And if I varied the input to the decoder, basically if I start out and just keep varying the z that goes to the net portion of the network that reconstructs the input, it can only reconstruct points on the blue line, right? Regardless of the input, it has learned to reconstruct outputs as some extensions of some basic pattern. That is the only pattern it can reconstruct. It cannot reconstruct anything else, right? So this happens. Now here's the interesting bit. In the original setting that I had a few slides ago, I said that the weights that go into the detector must be the same as the weights that come out, right? Even if I release that restriction, and I say that the input weights are W and the output weights are U, find me the W and U such that the error between the reconstruction and the original one is minimized. You are still going to always find the principal direction, because that is the direction in which most of the information and the signal actually lies, right? So U is always going to be the principal or some scaled version of the principal eigenvector in this case, right? The minimum error direction is the principal component. Now let's go to something more complex. Instead of going down to just one dimension, let's say I go into multiple dimensions, right? If I go into multiple dimensions, I have multiple perceptrons in the middle, multiple neurons. I have a weight matrix going into those neurons. I have a weight matrix coming out, right? And basically, I want these guys are feature detectors, and the upper portion of the network is the portion of the network that reconstructs the input in terms of the features that have been detected in the input, except that my feature detectors now have linear activation, right? So if I try to minimize the error between the input and the output of this network, which is x minus w transpose wx, the squared norm of this, then basically this again is just principal component analysis, right? What will happen is that the output of the hidden layer, you're trying to find the principal subspace, the planar subspace in which most of the information in the signal lies, and then afterwards you're going to reconstruct the input as being on that principal subspace, right? Very simple. I mean, this is obvious. If you've done pre-CA, you know this. If you've done any machine learning, you don't know this. Even if you don't, this has got to be obvious. You're just finding the principal subspace that the data lie on. Now, so I'm going to add this term. There are two components to this network. The first half is the encoder, which finds the position on the principal subspace, and the next is the decoder, which transforms this position into a vector in the original space itself. So the encoder is the analysis net, which computes the hidden representation, and the decoder is the synthesis net, which recomposes the data from the hidden representation. And here is the now this was what we had when we had linear activations. When we had linear activations, we were trying to find a planar subspace within which the most of the information in the data lie, right? What if I put in a nonlinear activation? When I put in a nonlinear activation, then you're no longer trying to find a planar subspace. You're trying to find any surface such that most of the information on the data lies on that surface. So in this case, you would end up performing something like a nonlinear principal component analysis. If that was the scatter of your data, you would expect to find that the hidden variables, the analysis over here in the hidden layer is finds the position along this curve, and then the recomposition actually reconstructs the original data from the position along this curve. So the data, the decoder represents the best nonlinear manifold to represent to fit the data. Now what this means is that suppose I trained a network of this kind, and then I got rid of the encoder and only fed various values to the decoder portion of the network. The decoder is only capable of creating points on this curve. So regardless of what input you provide over here, the output is going to be on that curve, on the nonlinear principal manifold, right? Now, the shape of the manifold, of course, now depends on the network. So the deeper and more complex your encoder and decoder are, the more complex these manifolds are going to be, right? But here's the interesting thing. Neither the decoder, there is no necessity for the decoder and the encoder to be the same architecture. I can have an encoder which finds a position on the manifold, and what the decoder is really doing is reconstructing the input based on whatever position I found on the manifold, right? So yes.
For the nonlinear autoencoder, because the PCA need to orthogonal transformation, but orthogonal vertical transformation, but the nonlinear.
No, hang on. We are finding the principal subspace. Yeah. Standard PCA imposes orthogonality of the basis as an extra criterion. So if you were just doing standard PCA, if you go back to slide number 70, PCA is not, if I just optimize this objective function, right? Yeah. There is no guarantee that the columns of W are going to be orthogonal to one another, yeah. But there is a guarantee that the subspace that W represents is going to be the principal subspace. In PCA, you impose the additional constraint that the columns of W are orthogonal to one another.
So if we add the nonlinear activity function, it will not be the same as PCA.
You're still trying to find the principal orthogonal subspace. You're not finding this. So even with the linear stuff, you're finding the principal subspace, not the principal, but not necessarily the basis along the principal subspace, right? So in that sense, you will still be finding, you would hope to find the principal manifold, but the basis within the principal manifold can be anything, right?
I have a question about, there's some people claim that their autoencoder is more like ICA, independent component analysis. Do you think this is more like PCA or ICA?
So this is, you're finding the principal subspace, right? Within that, now typically when you perform ICA, you actually find your first step is to do a PCA and then to find a different set of bases within the principal subspace. So those would be additional constraints on top of the basic framework. In ICA, the first step is usually PCA, so you bring it down to the same dimensionality as the number of output components you're trying to detect, and then you have a second step which recomputes the independent bases within the principal subspace. So those are going to be additional constraints. You could do that, for example, by imposing constraints on the Y. Right? Anyway, so this is a kind of a nonlinear, you can, again, it's intuition because these are optimization problems, but you can expect to find something like a nonlinear principal manifold. And deeper networks can capture more complicated manifolds. These are what we call deep autoencoders, right? So here are some examples, trivial examples. These are two-dimensional input, and you can see that the data kind of lie on a helix, right? If I try to find an autoencoder, which goes down to here, I have two hidden layers of 100 neurons, but the hidden representation is one-dimensional. Then observe what happens, that the output, which is given by the purple and the colored dots, that kind of almost captures the helix, right? And specifically, you find something strange happening, that although the data are scattered like so, now suppose I just compute this output. I train this network, and then I get rid of the encoder and vary what is fed at this point to the decoder from -1 to 1. That is given by these dots. And you can see what happens is that once I go outside the specific portion of the space where I found training data, it no longer actually continues to go in a helical pattern. It actually goes off straight, right? So you only learn to represent the data typically within the region that you've actually seen the data. And if you want that to be a meaningful representation, you typically impose additional statistical constraints on this hidden variable, which will give you a variational autoencoder, which you will hear about after the break. Here are a couple more examples. These are much narrower examples where the data clearly lie on a spiral in the first case, and you can see what the network has actually learned, right? You can see we didn't give all of those data as an input, but we gave just some part of it, and the network sort of learns to go from the output and learn a spiral. But the spiral is not actually following the actual structure of the spiral, because you have no control over how it behaves in the region of the space where there are no training data, right? So what happens is, suppose I train this network, then get rid of the encoder and keep modifying the input to the hidden representation. The output ends up looking like so. It starts off outside the spiral and then comes in this way, and observe that it doesn't follow the spiral, jumps across and then follows the spiral the other way at some point, right? So it's not actually capturing the structure as you would like it to capture it. You have to impose additional constraints on the hidden variable. That again is what we will do with variational autoencoders. But you get the basic idea. It's actually capturing some sort of a nonlinear principal manifold that the data actually lie on. And this is something, so when the hidden representation is of a lower dimensionality than the input, we often call it a bottleneck network, right? Learning the principal manifold. And this is something that we can use. The decoder can only generate data on the principal manifold that it has learned from the training data, right? So now if I take the decoder and keep varying inputs to the decoder, the output is always going to lie on the principal manifold. Now this is magic, right? Because what does this mean? The decoder is now a generator that's specific to the class of data that the network has been learned from, provided it has been properly learned, right? Any values applied to the hidden input will produce data similar to the training data. I don't care what it is. So this has an interesting property, right? If I took the full network here and say I trained a network on some class of data and I gave it as an input a completely different class of data during operation time, right? After it has been trained, it's going to convert that completely different class of data into an instance of the data from your initial class. So here's an example where, so here for example, the decoder would represent a source specific dictionary, generative dictionary, where feeding it any input is going to generate digit like patterns, right? Or more interestingly, here's something that we did. We actually trained an autoencoder on music, little segments of music. So this one was trained from a saxophone. And now we have an encoder and you have a decoder. Then I get rid of the encoder. If I feed any input to the decoder, the output is going to sound somewhat like a saxophone. In fact, once I train it, even if I feed piano to the network, the output is going to come out sounding like a saxophone, because that's the only thing the decoder can generate. So here, in this case, yeah, let me play this. This is, we set all of those values to 1, and that 0 and that 1 value to 1, and here's the sound that it generates. So when I say generate, it generates a spectrogram which can be converted to sound, right? We've been working with spectrograms. Or here's another. These both sound like saxophone sounds, right? Now here's an example where I learned something from a clarinet. They kind of sound like clarinet sounds. They're not notes, they're clarinet sounds. This network, once trained on a clarinet, can only produce clarinet sounds. And here's a, we actually, there's a very cute little application for something of this kind, which is meant, which should give you an idea of the kind of manipulations you can perform once you realize what really is going on, what kinds of representations are being learned. I'm going to try to perform signal separation. You're given a mixed sound from multiple sources, and the idea is to try to separate out one of the sources. So here, this is a standard dictionary-based approach. So the basic idea is that you're going to say you have different sources that you're mixing. You'd learn a dictionary of building blocks for each sound source. So let's say you have clarinets and pianos playing together, right? Or people singing and music in the background. You want to separate the singing from the music in the background. So you would first learn a dictionary for, say, in this case, I have a guitar as an example. You would learn a dictionary for guitar sounds. You could do this, in our case, by using an autoencoder, feed it lots of guitar sounds, learn to autoencode. Afterwards, the only thing this can produce is guitar sounds, right? I can learn a dictionary for the other source, which is in this case drums. In my example, I give it lots of drum sounds. I learn an autoencoder. The only thing this system is now capable, the network is now capable of producing are drum sounds. And then now we know that when I have a mixed sound is a composition of the guitar sounds and the drum sounds, right? So, and furthermore, I can assume that the guitar sound lies in the guitar manifold. It's been composed by entries from the guitar dictionary. So also the drums have been composed by entries in the drum dictionary. So the overall final mixed sound is a composition of something generated by the drum dictionary, something generated by the guitar dictionary, all mixed together. So this is going to be something like this. A composition from the guitar dictionary, a composition from the drums dictionary, all added together, gave you your final music, right? So now suppose I gave you the mixed music, final music. I can reverse the process. I have my dictionaries, but my dictionaries are just autoencoders, right? I have to learn what the input to the autoencoder was to produce the specific guitar sound that went into the final sound. I have to learn what the input to the autoencoder for the drums was to produce the specific drum sounds that went into the final sound, right? And that I can do just using, so here's how you could do this. I can have an autoencoder dictionary for each source, operating, for instance, on magnitude spectrograms. For a well-trained dictionary network, the decoder dictionary is always highly specialized to signals from that source. Then when I get the mixed signal, I'm going to provide the signal at the output. In the standard mechanism, when you perform backprop, you're learning the parameters of the network. There's nothing magical about the parameters of the network. I can fix the output and say, learn the inputs to these two decoders, the first of which can only produce guitar sounds, the second of which can only produce drum sounds, such that when their outputs are added together, I'm going to get the mixed sound, right? And once I've done that, I can just, the output of the first decoder is going to give me the source for the sounds from the first source, and the output from the second decoder is going to give me the sounds from the second source, right? So let's see if this actually kind of works. Here are some example results. This is a the next one. Yeah. There's the mixed sound. So it sort of cleanly separates it out, right? It's learned to actually, it's not clean, I mean, it's not perfect. The first guy, so yes. Yes. Pardon me? So the encoder decoder have been trained separately on the two individual sound sources, right? So now this decoder is only capable of producing sounds from, I think I have a clarinet and the sax over here, right? This guy is now only capable of producing sax sounds. So one of them is trained on clarinet, the other is trained on sax. And then when I'm doing the separation, I'm providing the at the output, I'm providing the mixed sound, and back propagation is learning these eyes such that the output there best matches what I just heard. And then once you find the eyes, then you can just capture the output right here, right? And those are the separated sounds. So that's what we have over here. This is the original in these cases. It's a 5-layer dictionary with 600 units. So you could hear the original and the separated. They're not exactly the same. For the second source, it's pretty close to perfect. right? Anyway, moving on. So just wrapping up, what we the lessons for the day: classification networks learn to predict a posteriori probabilities of classes. The network until the final layer is just a feature extractor that converts the input into linearly separable to being almost linearly separable. And the final layer is a classifier or a predictor that actually operates on these linearly separable features, right? And on the other hand, you can also think of the neural networks as being as learning dictionaries, as pattern detectors, which can in turn be thought of as pattern constructors. So you can think of this as learning, performing some kind of nonlinear principal component analysis, finding the principal manifolds, nonlinear manifolds on which data lie. Those are autoencoders, which can be used in turn to compose constructive dictionaries to model data distributions. Now, the basic autoencoder format has no constraints on how it's learning stuff, so its ability to extrapolate outside of the training data itself tends to be limited. So in the examples that I gave you, obviously these are cherry-picked and that we did a lot of tuning. But we wouldn't have to cherry-pick and we wouldn't have to tune if we impose constraints on the hidden representation, on the distribution of the hidden representations, in which case the whole process would be much more natural. You'd get exactly the same kinds of results. That's something Tom's going to be talking on immediately after the break. So I'm the next week spring break. The week after that, I'm going to be away in Tunisia, and I come back the week later. All right. Questions? Thank you. How do I turn this off?